Welcome back. It's a bit cold out there, but it's not so bad. I mean, spring's about to come. So, if any questions that I can. So everyone know how to have access to the class link. So let me know if anyone still don't know how to have access to those class website, because it's crucial because everything important will be uploaded there. It's literally once a week, the updating. So it's important to know how to have access to those. So what we did yesterday, we introduced you guys two different data examples. First one was the time series plot of so-called S&P 100 data index, and nothing but the measure of those price changes in average sense. So how high and low it can be changing over these years. You update it daily basis, so that what you can do is basically try to understand the underlying trend in these price changes, so that hopefully you can come up with some reasonable degree of forecast of those future realized stock prices. Second one, for the cross-section data rather than time series. So the index here was the how fast those national income changes as opposed to how fast those population grows. And certainly there's some relationship between these two. Turns out to be quite negative. We first plotted these data plots and try to understand what's the general relationship between these x and y. Turns out to be rather negative instead of positive, which is quite counterintuitive. And then we try to hook it up into some baseline economic theories in so-called family economics, saying the rising price of raising kids, especially in this urbanized society, might have some dampening effect of having more babies as the income rises. So that's where we stopped last time. Nothing fancy, just some intriguing data examples that so motivation was to help you understand what those processing data is like in practice. And you get to handle many of these data sets in practice, try to process them. At the end of the day, you want to get some important meaning, lessons out of these, so that you can apply to many different things in practice. So that's where we stopped. So real statistics stuff basically starts from today. It doesn't hurt to start with defining some important quantities first. Population. Textbook definition of the so-called population. So this is an important term in statistics. So since it's our officially first time to introduce this one to class, we better define it first before we move any further along. So it's defined as the set of all well-defined objects and elements of interest under investigation. What a rather boring textbook definition, but what we really mean it. So everyone knows what set is. So if you say that this, you know what set is, mathematical set. So mathematical set is something like this, collection of numbers. So it could be one example of sets, a very simple one. And there's also what's called a subset, which we will be using in defining this second quantity, so-called a sample. Subset of this original set could be any elements of this, and then you create a second set based on that. One example is this one. So both of these elements must belong to this mother set, but size-wise, the second set is smaller than the first one. So this is just a mathematical set, and this one is a subset, which belongs to this first set. So population is just a set like this one, but then it's much bigger than just the 5 elements in it, because it must include all well-defined elements inside. So the key word in defining this population is this word. Should be everything in it. Example of population could be all the residents in the city of Seoul. It's a pretty big number. What's the exact size now? Over 2 million, I guess. So very big number. Other population could be, I don't know, engineering students here at Hanyang, because engineering school is certainly the main body of this university. So something big. So it's fairly difficult to track down all those elements one by one. So you get to depend on so-called sample instead of population. So if you want to measure the, say, average height and weight of all those, I don't know, incoming first-year students here at Hanyang, size-wise, that's still big, like a 4,000, is it? how many students coming here every year? 4,300, something like that, some big number. So the best way to figure out what those average heights and weights are, you basically ask around one by one. We're talking about 3,000 people. So it takes too much time, energy, and efforts and resources, so we just don't see its value doing it that way. So instead of asking around every one of those 3,000 people in the population, we hand select some of them, and then call that as a sample, and then ask the sample members instead. So the samples could be like people here, like something like a manageable, tractable size of 20 or 30. But then the question is how do you select those elements out of population? That's a big issue. So the sample should be representative, should reduce the potential bias that you might introduce by selecting them. There's some other delicate issues in formulating or getting the reasonable sample, good representation of the underlying population, but that's much beyond the scope of this course. So we just put that aside for the moment. But definition-wise, these are just basically what we mean. Population must include every element in it. Sample just a subset of the population, much smaller in terms of size, but more manageable and tractable, so they can, characterize it, processing some information. So example is randomly select some 10 students from the underlying population, whatever that might be in practice. Very important terminologies. In practice, we never actually get to process anything about this population is because this one is too big. But pretty much every time we have to processing those data, it's all about this sample because that's what we are having in hand. You cannot process something that you don't own it, but data set, sample is, we are having it, so we can process it and then treat it so they can come up with some reasonable outcomes and conclusions from those. So that's population and sample. Will I ask this one on the exam? Of course not, because it's too simple. We just understand what population is and what the sample is, what's the difference between the two, and what we really mean by saying either population or sample, and that's about it. Not much other than those. So after you're getting these samples, what you want to answer is some of those important characteristics of this underlying population. Getting back to the example of the average height and weight of all those 3,000 incoming students here at Hanyang, that's one kind of important characteristics. How high and how heavy they can be could be interesting to some people. So you might want to figure out what those numbers are. And those numbers actually may not be numbers, could be just simply category. One example of those categorical characteristics, like a student's gender. You know what a gender is? Either male or female. Nothing in between, almost always. So either category 1, the female student, category 2, which is male student. Or it could be a quality of certain product. Everyone carries around smartphone these days. You might want to categorize into excellent quality, mediocre quality, or bad one, so that you have to throw that one away. So this is certainly category. But when you actually process these, you have to assign some numbers to it, like a number 1, well, maybe number 2 to this excellent category, number 1 to this mediocre one, and number 0 to the bad one. So they can actually compute using those numbers instead of just dealing with these categories themselves. In contrast, these characteristics can be numerical as well. And by numerical, we just means a continuum of real numbers. Any real number between 0 and 10. That's an example of numerical category. So, numerical values, numerical characteristics. So example could include heights of a students. Heights are real numbers, anything between 0 and, I don't know, at least in theory like a 300 or something. Value of a stock or stock price or price inflation could be an example of those numerical characteristics. Many more. But the important thing is that you have to see the difference between this categorical and numerical. Numerical, you cannot fill in the gap. So if you talk about the height of a student, it could be like if the metric works in the centimeters and meters, could be like something between 160 to say 210. So pick up any two numbers in this interval. First one here, first one there. You can always manage to find something in between. So there's something in between here. And if you pick the middle value, it's not exactly middle, but somewhere in this, between this and that. And then now you can always pick another number between this guy and that guy. Right there. And then you can keep repeating it. And there's no way you can stop. You can always find some values in the middle of this range. But that's not possible under this categorical case. Either good or bad. Something between 0 and 1, there's no such a thing. I cannot imagine somebody who's neither man or woman. Just has to be one of them. It's a specific category, nothing in between. So you cannot possibly fill them at all. So that's what's called the categorical ones. It's just different natures. But at least definition-wise, that's what we mean by those. Okay. The similar to the characteristics, the so-called variables can be also categorical numerical. First, we have to define, since it's the first time that we introduce this term. What is variable? Any characteristic that might change. So the key term here is this one. It has to change. Either over time or over other criteria, over some objects in the population. If you focus on the height of like 100 different students in the sample, they all have different heights and weights, so those number changes. Notation-wise, sometimes it's represented by these lowercase characters, letters, could be capitalized sometimes. There's a subtle difference though. When we have to denote them by uppercase, and when other times we have to denote them by lowercase. Does anyone know the difference? So if X is the height of a student, sometimes it's capitalized like this, other times it's a lowercase. What's the difference? The capital one usually represent the variables themselves, but the lowercase is just the numerical values taken by those. So X could be like 170. That's a number, not a letter. So that one is taken up by this lowercase, which means that this number can possibly be taken by this bigger X, but not necessarily that specific value. It might change because it's a variable. So these little x and little y and little z typically are some numerical values, numbers. But these uppercase X and uppercase Y and this capital Z, these are not numbers. It just has a meaning. So definitions like a height, weight, or I don't know what the third could be, like a wealth level or something. But you can name them. So that's a variable. The key thing is that it must change over certain criteria. If it's fixed, we don't call that as a variable because it's completely predictable. Okay. Types of data can be also categorical and quantitative or numerical. Just the same way the characteristics and variables can be. Nothing very fancy. And something more involving coming up. So this descriptive statistics and inferential statistics. In order to explain what this descriptive statistics is about, it doesn't hurt to introduce some simple example. Let's talk about the demand equation. So whether it's a descriptive or inferential, it just represent the two different approaches that people typically take in order to understand what the real underlying relationship is. So one example of this descriptive statistics is dealing with so-called demand equation. So typically in the demand equation, there are two key variables. Some changes over characteristics, criteria, I mean. So the left-hand side, typically we have some sales data. Could be like automobile sales. On the other hand, some other variables might have some important recognizable impact on this one, typically income. makes sense. I mean, how many cars, new cars will be demanded in the market certainly be affected by how much income people have. If in general income level goes up, the demand for cars, automobiles also increase. So one simple way to define so-called demand for automobiles. You all know what automobiles are. Cars, basically. Many other important factors, but for now we just put them aside because we cannot bring in on all those potential factors together because it's just elementary level still. So if you linearize the relationship, could be some intercept, could be some slope, and all the rest. So that's the simplest possible way to formulate so-called demand equation. Stand it this way. What's the name for this guy? You have a specific name for this beta 0. So this notation reads as beta. You read it as beta 0 and beta 1. It's some Greek. Language in Greece. But why Greek? Those ancient mathematicians are all Greek, so they started calling those. So what do we call this beta 0 in mathematics? It's called the intercept. So that's the name. So name of this one is intercept. And the coefficient here is typically called as slope. Picture-wise, you can imagine any linear line. And any linear line is supposed to cross this y-axis. And that intersection, the specific point here is called the intercept. And then the slope represents how much change in y you can expect when you just increase x by 1 unit. So imagine that the x, in this case income, increases by only 1, whatever the unit might be. There should be the corresponding change in this y under this curve, and that's this. So how much increase in this y, given this unit increase in x, that's represented by this slope coefficient. Elementary school algebra. So you all know it. So just the different names. But pretty much often in economics, instead of simply represent the automobile sales in terms of this household income, people typically take the logarithm of those. So instead of that, pretty much often they do this. You all know what log is. What's log? It's the name of a function. If you graph it, if you come up with a graph of log, shape of that thing is something like this. What's the value here? Somebody said something. Who said it? 1. Yeah, very nice. It's 1. Notation-wise, there are 2 different logs. If you just simply write as a log and don't say anything about this base, typically this one means base 10. Right? But there's a second kind. Instead of writing as a log, you might simply write as ln. What's the base here then? E. What's E? Exponential. Some number. Don't have to know what it is. Just know that there's something like that. So that one is called a natural log. And this one's called a base 10 log. So name-wise, that's a natural log. And this one is a base 10 log. It's just the same function but different base values. The first kind of logarithm use 10 as the base. Second kind use as the exponential. Why is it called a natural log? Beats me. My guess is this kind of the logarithm is much more popular in natural science than in social science. Maybe that's why, but really, I have no idea. So nothing natural to me, but whether it's a natural log. But the different notations, if you write it as a log, implicitly means that the base value is 10, but if you instead write ln, it implies that the base value for this one is exponential. But whether this or that, the shape is still the same. So after introducing this logarithm thing, now the question is, why do we do it? What's the point of just the transforming everything into log? Why don't you just simply look at and collect the data for how many cars were sold in the market in specific time, and then relate that to how much money, how much income each representative household in certain economy has yearly basis? Why do we bother to take log of both? I mean, even if we write it as simply it says here, some unknown intercept, unknown constant or slope, multiply this one by amount of household income, that's perfectly valid demand equation. But why do you bother to take log of these? Because you have a free time? There are two reasons. First one is a completely mathematical and statistical. Second reason is much more economical. Anyone know why? What does taking log do to us? What's the range of this household income? So in US dollars, that's typically something between 50,000 per year, could be like 200. We can translate that into Korean won, but the number gets a lot bigger, so we want to keep it more tractable. So typical range of those annual household income in the U.S. something above 50,000 per year for the entire family, and it can go up to like I don't know, 200,000 or something. Could be up to like a million, but that's more like outlier. So numbers are huge. 5 times 10 to the 4th. Talking about the bottom value. If you go up to the top, that's 2 times 10 to the 5. That's a very big number. But if you take the log of them, what happens? It's the value of log of 50,000 if you use the base 10. What's this? 5. So this one multiplied by 5, or actually 4, because that's 10,000. Wouldn't be so much different from this. So the point is that if you deal with this annual income in just a raw sense, raw data, numbers are too big. So you want to shrink the range by taking log of them. So if you take the log of these numbers, something in between these two huge numbers, that's typically something between 0 and 10. Much more tractable and manageable. So that's one reason. You want to narrow down the scope, range of those values in some tractable way. And that can be easily done by simply taking log. A purely technical reason, nothing economical, no, so intuition going on. It's just a simple technical stuff. Numbers are too big for our data sets, so we want to shrink the range. And that certainly helps us in terms of computation. Similar to this automobile sales, if it's a major manufacturer like a Hyundai or Kia, number of cars that they manufacture in their factories could be very large, like 1 million. So you can simply bring it down. Shrink the range by simply take the log of them. So So you work for both. So that's the first non-economical reason. Second reason is much more important. So talking about why we have to bother to take the log of this both sales and household income. Number one reason is because you want to deal with smaller numbers, so that computation becomes a lot more manageable, easy. So that's first one. Second reason has to do with some economic concepts. If you pay attention to the meaning of this guy, we are not so much interested in this constant term because it's just some number, could be negative or positive. There's no real economic meaning into it. But this one is something significant. So meaning of beta 1 is nothing but a ratio. That's the meaning of beta 1. And the little delta here refers to change. Name of this notation is not triangle. This one is called the delta. Again, it's Greek. A lot of Greeks in mathematics. It's just the name of it, like A, B, or C. So if you see the little triangle in mathematics, that one is typically called as a delta. Means change. Since it's a variable, it should be changing. And how much change we are having? We are having change as much as this delta. But should be small. Where do we get this equality? How do I know that that's the meaning of this beta 1? Well, it comes from its definition. Going back to the linear line, because the whole equation is linear, if you have a x down on the horizon, y upon the vertical one, so imagine that there's some straight line passing through. So intercept is here, that's beta 0. And beta 1, like I said before, first increase this bottom x by only 1. And then there must be corresponding change in y, which is measured by this increase. That's basically beta 1. And that's the definition of slope of any straight line. So you might think of like equations like this. Y equals negative 10 plus 3 times x. That's a simple example of linear equation. The number 3 represents, if you have an increase in this x only by 1, expected change in y is 3. So that's what this is. Given this, whatever the change you might have in this x, first figure out how much change, and then you go for the y thing, and then figure out what's the amount of corresponding change in the second variable, divide the second change by the first change, and that becomes the slope. It's just that x in this case, log of this income, y in this case, nothing but log of sales. That's why. That's all. But what's crucial is the next step. So eliminate all this. So we all now know what this delta thing is. Let's figure out what this is. So now the notation changes this wiggly thing. So if you just put those horizontal two bars, top and bottom, that means the relationship is exactly the same. But instead, if you change it to this wave thing, both top and bottom, that means approximately. It's not exact. So moving from here to here is 100%. Will certainly happen. But moving from here to whatever comes up here, also above 90%. Something approximate. Not even close to 100. Not really exactly the same. This one can claim that nothing but the change in sales divided by sales itself, and put bracket in order to avoid any confusion. Repeat the same procedure for the bottom part. Now the variable changes from sales to income. Delta income divided by income itself. It's just two different fractions. One fraction at the numerator of this entire fraction, second fraction here at the bottom. The variables are different. Here at the top we deal with sales, here at the bottom we switch it to income. But what on earth makes us move from here to here? And that comes from the property of this logarithm. Do you know calculus? Everyone has taken at least 1 or 2 semesters of calculus back in high school. You don't know what calculus is? Never ever heard of calculus? Oh, it cannot be. But don't you have to take the math exams when you take the college entrance one? I mean, it's a simple equation like this. Y equals defined as 3 times x. What's the differential of this y in terms of x? Didn't you compute things like that? Yeah, you know it. Yeah, that's 3. So that saves me. I panicked. So you know it. What happens if the function becomes logarithm? What is the differential then? Anyone? It's a 1 over x. Oh, it's x. I was writing something nothing. So this is x. Yeah, it's just a property. If you want to verify, go back to the definition of those limits and everything. You can derive the whole thing from the beginning, but you can trust me on this. I did it like 1,000,000 times. So if you differentiate this linear relationship, change in y in terms of change in x, the corresponding number is going to be 3. But if you repeat the basically same procedures for this nonlinear logarithmic function, the change in y divided by change in x is nothing but 1 over x. So where do we get this approximation? Simply because of this. Because if you rewrite the whole thing, so in principle this is just nothing but ratio. dy over dx equals, happens to be in this case 1 over x. So you can move this bottom part to the other side. But then the relationship is nothing but this. Right. So simply take this dx at the bottom here, move it to the other side, then it will be located at the top, and the whole thing becomes that. dy equals dx over x. What's y in this case? Log of income. That's y. What's x? Oh no, I'm sorry. So y should be log of the automobile sales, and x is the log of income. So if you replace this, delta is the same thing as d thing. So that's a delta or d in log of sales. That's basically this dy here. But you do know that that's nothing but dx over x, and that's exactly this. So this delta is the same thing as d. It's just a more fancier notation. This d and this delta and this d is basically the same. But then the whole thing at the top here is nothing but d this. but that's y in our case. So by this relationship here, we can replace this d or delta in y by this d or delta in x divided by x. But x in our case is log of income. That's why. Log of sales, I mean. Wait. Oh yeah, exactly, here. Okay. So first work on that same thing in terms of sales, and then switch it to income, and you get this relationship basically. Right. But moving from here to there, it's just a mathematical manipulation, but implication is actually huge. What is this? Not to lose any generality, just multiply the top and bottom by 100. It's alright because you are doing the same thing at the top and bottom because they kill each other. But if you multiply the top one by 100, what's this? That's a percent change. Percent change is the change in certain quantity, divide the change by its previous value, and then multiply the whole thing by 100. That's percent change. Percent change in car sales. And same thing down here, change in income divided by income itself, and then multiply the fraction by number 100. That's also percent change now in income. Then what is this circle thing? What's the name? It's elasticity, income elasticity. It represents, it's a small number, some number like a 2 or 3, given like a unit percent change in this household income, what should be the expected corresponding percent change in the car sales? Shows how elastic that automobile demand is. If number is big, we say that the automobile demand is very elastic, but if the number is down, low, we say that the market is very inelastic. Demand is very inelastic, not elastic at all. What's the sign of it? So the exact number for this quantity, so-called income elasticity, we don't know. We never ever get to observe the actual value. We have to guess it using the sample in hand. But then we can at least guess about its sign. What's this expected sign for this circle thing? Positive or negative? So positive means it's a plus. Negative means it's minus. We can at least say its sign. What's the expected sign of this? Why? So it's certainly positive. Why is it positive? Or just say what you believe, and that's fine. Give it a shot. What does this one represent? It basically represents, given some increase in your income, there must be some corresponding change in this automobile sales. We are saying that by saying this, that increases. So with a rising household income, people get to demand more of these cars, which is perfectly common sense. It's true. When your income goes up, people demand more of those cars. Period. You don't need to be a rocket scientist to figure that one out. It's just a common sense. Everyone knows that. But is it always positive for every product that you can imagine? No. What are some of those few exceptions? This number can be actually negative. So in the automobile case, certainly positive. If you, when you get more money, you go out and try to switch for better and newer cars. So demand goes up. But if you imagine demand for things like ramen noodle, when your income goes up, I wouldn't eat it. I mean, what's the point of making money? you want to go out and enjoy better meals. And so it's only the case when your budget is really tiny. You might settle down with those ramen noodles, but otherwise no. Other example could be like McDonald's. Nothing against McDonald's, but fast food places, I mean, not that popular for those billionaires and millionaires. So there's the funny joke in economics. You know what business cycles are? So there's a term called the business cycles, running out of space. What's business cycle? So it's a combination of business and cycle. But if you put those two different words together, some economically very meaningful thing can be defined. What's business cycles? Have you heard of the term recession? No? Have you heard of the term economic boom? What's economic boom? So in simple way, everybody's happy. That's what economic boom is. Many jobs around, the income level rises, there's more demand, and supply increase, try to catch up with rising demand and everything. Like GDP goes up, plenty of jobs around, college graduates have no problem getting jobs right after graduation. Things are going very well. Businesses, sales increase, they want to expand more. Like not quite these days, but it used to be like end of the 20th century, like late 19s or very beginning of 2000. The opposite is recession, so everybody's unhappy. So no jobs around, people get fired, they lose jobs simply because of those downsizing. So there are cycles. So those business conditions, economic conditions, sometimes good, so-called economic booms. Everything is turning very okay and good. But sometimes, some other times it's just down, very bad. And they keep coming in repeated fashion. There's no exact period, but we do know that if you have some brief period of economic boom, we do know that certainly will be followed by some recession down the road. If you are going through that bad time, recession, we certainly believe that it will be followed by some second economic boom and so on. So forecasting those business cycles is a huge task to macroeconomists because it's an important issue. I mean, if there's a recession coming up, you want to prepare in advance. So you have to forecast. So the GDP or national income account is gonna turn down in the next 6 months or next 12 months. That's the job routinely done by those staff at the central banks. So here in this case, Bank of Korea. They run those tens and thousands of different fancy economic models to forecast those cycles. When will be the next recession, bad times, and when will be the next good times, so that business owners can use that information to either expand or shrink their businesses. So one very reliable indicator of this business cycle is McDonald's sales. So because the sale goes up, it's just pretty much good indicator of the bad time is coming up. People prepare in some sense by rationalizing their budgets, but if the sales goes down, it means that the things are turning around pretty good way. Don't take it too seriously, just an example of those, how people try to forecast those business, like many different indexes, but one of them could be like a sale of those inferior goods. So if this computed quantity, given the certain amount of change in your income, what should be the expected response from the market? Change in the sales, in this case automobile sales. If this number is bigger than 0, we call that as the normal goods. So if the computed elasticity happens to be a positive number, we call that such a good as a normal good. Simply means that with a rising income, people get to demand more of it. One example is automobile. Second example could be house. Third example could be, I don't know, jewelry, something expensive. But inferior goods is the opposite, something like a ramen noodle or something. So all I'm trying to say, figuring this number out, how much response we can expect in the market sales, demand, given this unit increase in the household income, is something economically very important quantity. We want to know it. So such a lengthy way of answering this question, what is descriptive statistics? Computing numbers like this. That's descriptive statistics. And many other examples. Since this is the prerequisite of the sequel, which is called econometrics, nothing but analyzing those bunch of different economic or statistical data sets, try to hook up to those economic models and some storytelling. Certainly important to explain those definitions in some economics context. So one of those examples could be these elasticities. Economically very important, crucial quantity. Nothing knows the exact value. Nobody knows the exact value because it's not known. So you try to guess, try to estimate it. And the whole procedure of estimating number like this one is called the descriptive statistics. A lot of mathematics. So textbook definition of this first kind of statistics, descriptive statistics, deals with summarizing, describing important features. Important features in this automobile sales example would be elasticity of demand, income elasticity of demand, how responsive or how elastic those automobile demands are. That could be important feature to many, and we want to figure out what the reasonable approximate value for that unknown number, unknown quantity. In more simpler sense, those important features simply could be mean. We all know what mean is. You just add up all those corresponding numbers and divide it by the size of population. Or median, the value observed in the middle of the distribution, which we will define a lot more in detail in next week. Standard deviation, and so forth. So descriptive statistics, in a nutshell, there are some very important quantities that we want to figure out, but it's just unfortunately not given to us. So you have to utilize so-called data set to figure out or guess about those unknown numbers. One of those examples is elasticities. And many other more important examples can be found in practice. So far, so good? Everyone's with me? Any questions that I can? Anything so far? I know that you have questions. You're just thinking about whether should I ask it or not. Yeah. This one? This one? Yeah, this one. Don't understand why this is. This one? It's like your axis is gold and silver, or which one is it? I mean, you can come up and say. So just point it. What part bothers? This one. Yeah. Ask in Korean. Yeah. So you mean, given this property of logarithm, you don't know how to use this one to derive this relationship? Is that what you're saying? Think of it this way. This y is basically log of x. So different way to argue this. if this y is confusing, replace that one by log of x. It should be d log of x. Because y is log of x in this equation. We are saying that this one is equivalent to this. So all I'm doing from here to there, using the functional relationship between y and x. Y is defined as log of x, so just the d log of x and then the same rest. And I'm saying here, for the top part, x is sales. For the bottom part, x is income. So this guy, d log of x, replaced by dx over x, which is this. Now turning to the bottom part, now x is now income. So that's a d log of x, which is this one, approximately the same as d x in this case income and divided by income itself. Yeah, bringing this second variable y might be confusing, but y is defined as log of x. So y can be replaced by this quantity, and then that might help where this relationship comes. Thank you. Others? Why this is approximately the same as this? Well, because this is not d. Yeah, if you replace this one by d, everything is exact. But here the delta is almost the same as d, but not exactly the same. So d is a very small quantity, like a very small. But unfortunately, in this case, our delta still small, but not very small. Why is it not very small? So what I'm saying is that if you replace this delta thing, means there's some change by this d, same kind of d, then this equation becomes exact the same. Relation becomes exact the same. The reason why it has to be approximate is because we are not replacing this one by d, still delta is there. But there's a good reason why you have to stick with this delta, the delta thing instead of d. Why? Because of this change in sales. What's the typical value for this change in sale? Is it something very close to zero? Not really. So you record the amount of sale for a particular month, and then you update it by going for the same variable for the next month. There'll surely be certain some change, but number is not even close to zero because it's a car sales data. So if you manufacture like 1 million cars a month, you're talking about worldwide manufacturer like a BMW or Honda or Toyota, they produce huge amount of cars. And those sales or production fluctuates over a month. Sometimes it could be million, the second month could be like a 1.3 million. But if you take those difference for those two adjacent time periods, it's not even close to zero. Something actually very big. So it has to be estimate. And that's still the case after you transform everything back into this logarithm. Because say that, at 1 month, car sales for like a Honda could be like 1,000. You take the log of it, that's basically 3. But next month, the sale could go up to like a 10 to the 3.1 or something. But if you actually go down to this, computed number for this 10 to the 3.1, there's still some sizable difference because they're not even close to zero. Still, there's a sizable difference between this logarithm of these two huge numbers, which is a 0.1 in this case. Still small, but we can't argue that that's very small. In order to make this relationship exact the same, this delta should be literally like 0.000001 something. But in this case, that's certainly not the case. So we cannot really say that those approximation becomes exact the same. Because in certain sense, this is unavoidable, because all these things that we are getting from the empirical data set, there's no way we can control those values taken up by those variables. It just happens. But empirically, we do know that those, if you just track down those variables, keep recording them, there will be certainly ups and downs, but those changes in those two adjacent time periods, not even close to zeros. There's still some sizable difference. So that's why we have to bother to this sort of like approximation rather than exact derivation. So, okay. So that's the first kind. The second kind is a lot more involving. I'll just give you some general idea what this inferential statistics is about. So I might want to keep the model. So inferential statistics. So what is this one is all about? It's basically that. Basically this. Hypothesis or just claim. Hypothesis is too fancy word at this point. Claim 1. Beta 1 is bigger than 1. Versus second claim, which is claim 2. Beta 1 is less than 1. In both cases, those beta 1 should be positive. We all know it, because we're talking about the automobile sales. But whether it's bigger than 1 or less than 1, still we don't know. But why 1? Why not 10? Or why not 20? What is so fancy about this number 1? So basically what we are trying to do in this inferential statistics, come up with two different claims. Claim is unproved statements. You somehow believe that this is the case, while other people believe that that's the case. There's no settlement. People keep arguing. One group of people favor the idea that this beta 1 should be bigger than 1, but other people believe that not quite so. So these are untested, unproven statements about the nature of this beta 1 thing. And inferential statistics is basically a series of steps that you have to go through to pick up which one. So that's inferential statistics. Basically testing. Come up with two potential hypotheses surrounding this important quantity, so-called elasticity. So one claim about this unknown quantity, second claim about the same quantity. There are two candidates, and you are presented and asked to determine which one. And you have to pick one of them. And then the way to pick is not just simply coin tossing. You have to actually go through some sophisticated steps so you can come up with some reasonable answers. And the whole procedure is what's called inferential statistics. And how do you actually conduct this? It's complicated. So we don't do it now, but we just delayed. But we at some point in like the second last week, or maybe the last week of this course, we might bring in at least some introductory level of this testing and inference, but certainly not at the moment, because we are way out of that at the moment. But getting back to this question, why we have to pick this 1? What's the significance of this 1? If that's confusing, just think about the middle case. Say beta 1 is actually 1. Neither this claim or this claim. What's the meaning of this? So beta 1 is the same beta 1 up here. If the number for this one is exactly the same as 1, what's that meaning? Given that this one represents the demand elasticity in terms of income. If beta equals 1, it means your household income goes up by 5%. automobile sales increased by 5%. So 1 to 1, exactly the same percent change. So is it more than 5% or less than 5% should be great interest to company owner. He wants to know. I mean, it's certain that the income level will change in the next 6 months or next 12 months. So he wants to plan things ahead. If the income level is expected to rise because of those economic boom or something, he wants to invest more into his production line now so that he can jack up the production in the next six months. Something very important. But if the number turns out to be less than 1, just means that the automobile demand is not so responsive to those changes in income. So you might want to adjust the scale a little bit down. So certainly some important consequences follow, whether we decide that this is the case or that's the case. So if that's the rather unusual case, the quantity turns out to be exactly the same as 1, we call that sort of demand as a unit elastic. It's just a terminology. So the fancier term, basically saying the same thing. If the demand elasticity for this automobile industry turns out to be exactly 1, we say that the demand for the cars, automobiles, are unit elastic. 1% change in household income expected to bring about 1% changes in automobile demand. But if it's bigger than 1, we say that the demand is elastic. And the opposite case, if it's less than 1, we call that as an inelastic demand. So if the demand turns out to be elastic with those estimated value for beta 1 bigger than 1, you have to respond quick because the change in demand is going to be huge. But if this is the case, you can be a little bit slower because the expected change in this demand for those products is not going to be that much. So some interest to some of those people who are directly involved in this type of market. So it's important to know which one is the case. So official definition of this second kind of statistics deals with techniques for drawing inference. Inference is basically testing. Testing between those hypothesis 1, claim 1, or second hypothesis, second claim, or predictions about the population, of course based on the information, data that we obtain from those samples. So that's inferential statistics. We talked about much bigger picture. Now we're getting down to the detail. So some of the very basic, rudimentary descriptive statistics in practice. First one is a stem and leaf display. It let us know what the underlying distribution of those sample could be. Does anybody know what the meaning of this stem? What is stem? Oh, yeah, exactly. So if you look at a vegetable, like a spinach or something, so there's a main body of that vegetable. So that's called a stem. And then leaves are coming out of this stem. Not very good at drawing, but so these are leaf, but this main trunk is called a stem. You might have heard the word stem cell research or something. So why is it called the stem and leaf display? If you look at the picture of this one, it's crystal clear. So there are two different columns. First column on the left-hand side. So since it's the case of the height of students in inches, smallest guy in the sample is 45 inches, and largest one is 82. And then some other guys in the middle of them. The total number of students that you asked was 10. So if you count the number of these observations, that's exactly 10. In terms of its size, you can rank them, starting from the smallest one at 45, all the way up to the biggest, 82. But if you present the information this way, simple display in terms of its rank, it's hard to see where the peak of this distribution is and what are some of those outliers, potential outliers, But if you translate basically the same information here down into this kind of a stem and cell, stem and leaf display, it's much easier to observe things like that. So how to display this? First, starting with the largest value. Since everything is a 2-digit number, there must be tens digit and ones digit. So in terms of the number 1, the biggest one, tens digit obviously is number 8. So put 8 on the left hand side, and corresponding the number for ones digit is 2. And just basically repeat for each one of these remaining observations. And then you end up with this stem and leaf display. Some of the good things we can expect by using this one instead of just a simple display of the numbers like this one. It deals with actual values, and it's easy to see what's the exact extent of spread in the sample. Do you know what this spread is? So think about 2 different distributions. So distribution A could be something like this. Second distribution could be like that. For both of these distributions, the middle value are approximately the same. So middle value for both is somewhere here. But in terms of spread, there's a big difference. Which one's got more spread? A or B? B. Yeah, this one's got more spread. How, the diverse observations could be, there's a lot more because the range is just from here to there. But for the first distribution, the absolute majority of those observations are gathered in this tight range. So the spread is not that much. But one of the good things that we can expect by displaying this information, using this stem and leaf display, easy to see what's the amount of spread in this particular sample. Because the peak is around here, the 2 outliers are here at the maximum value, down to the minimum value of 45. So sizable amount of spread in this case, but if you just expose to this simple array display of these 10 different numbers, hard to see how much is spread. It just, unless you compute some standard deviation or something, it's just hard to see. But very simple and basic way, displaying the same thing in this stem and leaf display, you can instantly see how much spread you can have in this particular sample. Another good advantage is that you can expect by displaying this information using the stem plot, so easy to see where are some of those outliers. So outliers defined as any observation that tends to stay away from the mainstream values. So if you have a cluster of data points, so most of guys are around here in terms of like exam scores. The mean value for any exam, standardized exam, is typically 0, and the other end you have 100. But if the exam is not very differentiating, the most of those students gathered around in this medium range, but there could be like a couple of outliers. Hard workers, people never work, both are outliers. So that there's a saying that genius and idiots have something in common. The common thing is that both are outliers. So one is just in the good direction, the other is the bad direction, but they're still both outliers. So whenever these two guys stay far away from this mainstream distribution, the rest of these members, the rest of those observations in your sample, these points are called outliers. Is it good or bad to include these outliers in this data processing? Typically very bad. Why? One example could be, you know where the Seattle is? It's the name of city. If I draw the map of the US, there's a California, pretty part. If you go there and you don't want to come out of it because everything's so pretty. Florida is down there, Canada is up there, Seattle is right there. What is famous for Seattle? What people think of when the word Seattle comes? Rain. It literally rains 9 to 10 months. So a lot of people get like very depressed. Because, rain, day after day. It's not snow. I mean, snow is at least romantic. But rain, I mean, once in a while, that's not a bad thing. I mean, say there's a rain in one day and then very sunny for the rest of the week. Talking about 9 months in a row. So the parameter characteristic about the population in the city of Seattle, you might be interested in average income of all the citizens of Seattle. But who lives in Seattle? Someone famous? Bill Gates lives in Seattle. What's his net worth? 41 billion. So you have to include him by some bad luck. You have to include him in your sample. It's an extreme outlier in terms of this income distribution. So including him in your sample, it's basically scrub all those underlying distributions. So you don't want to deal with it. So anything extremely outlying the observations from whatever perspective you want to process your data, so that's usually a bad thing because it distorts the true relationship trend that you would try to estimate using those samples. So typically what they do, they first come up with this sort of or other sorts of display of those data set observations and try to pick up those potential possible outliers out of the sample and then go through some sort of test whether this guy is indeed outlier or not. Because if you just say if it's staying far away from the mainstream, that's outlier, but how far? It's not so certain. If you move this guy more towards to the median, somewhere here, is it still outlier? Or if you push it a little bit further to the mainstream, is it still outlier? It's hard to say. So you have to quantify everything, come up with some cutoff. If this observation goes beyond this point, this is officially outlier. But if it stays inside this boundary, it's still not outlier. So coming up with this boundary, you need to compute certain things. So that's the testing. So official way to process, the determining whether a certain observation should be outlier or not, you have to come up with, these quantities. But that's some other things that we'll discuss later. But there's a certain way to actually go through it, and then you can actually test whether certain observations should be called as outlier or not. More basic ones, so not so popular way to display these observations. A dot plot could be replacement of the stem and leaf display. So very simple. You just observe some data plots, data points, and then along this one-dimensional line, you just place it. So if the exact value for the minimum value is 45, you just place the dot right here in the middle of this range of 40 and 50. And then for each one of those observations in your sample, you just repeat the whole process and come up with these dot plots. Nothing fancy. Histogram is different kind. It let us know what's the underlying distribution. So getting back to the example of like categories, quality of your smartphone. If it's extremely good, you're very satisfied with its quality, you might assign number 3, which means that the quality is very nice and excellent. And 4 people believe it that way. So the size of this, the bottom, which is called the bean, represents the category 3 in this case. And the height of this bean represents frequency. How many people? 4 people believe it that way. So you raise it to this number 4. Second bean represents what's the quality of your smartphone. You think it's so-so. And there are like 9 people because it goes up to the number 9. 9 people should belong to the second bean. Third category means it's bad. So 6 people believe it that way. Rest of them is just a garbage. You have to throw it away. And only 1 person. But if you narrow down these categories, here we are simply dividing into 4 different groups, but you can increase the size of a number of different groups up to like 100. Then bean size gets very small. So the approximation becomes very accurate. So if you reduce the size of bean, So instead of just let you pick any number between 0 and 3, you can place your satisfaction into any integer between 0 and 100, like 100 different categories. But then pretty much what the histogram will look like is a very thin bin. Bin size is this, the size of this base, so it shrinks a lot more than this. So if you keep repeating those, constructing these bins, and connect these frequencies for each bins, the 100 different ones, you come up with a very nice and smooth curve instead of that very crass and rude one, a very choppy one, and that's called the distribution function, density function. That's one way to refine or estimate those underlying density using these histograms. I think I'll stop here unless you have any other questions. So when we come back next week, we start from this inferential statistics. First problem set will be posted up on the web by Friday, and you'll get email. And that one, don't turn in your solutions. I don't expect you to turn in your solutions. Just keep it to yourself. But what you can do instead, you just work on those problem sets over the weekend, and then the solutions will be posted by, say, Monday or something. Then you can compare them. But then the way we are going to use those problem sets through quizzes, which is subset of those actual homework questions. So, but those dates for those quizzes will be announced way before the actual dates. So don't worry about those.